is MGF 1107, Chapter 14, Section 3, Part 1. This section is going to have to be done in two, maybe three parts, maybe even more. A lot of information in here, a lot of example problems, and I'm going to try to take my time into making, this is called apportionment methods. Okay? And so first of all, on page 885, let's just look at this. It says the goal of apportionment is to determine a method to allocate the total number of items to be apportioned in a fair manner. It says one of the most important examples of apportionment is in determining the representation of governing bodies. However, apportionment problems occur in many other places, from determination of how many police officers should be assigned to each precinct in a city, to determine how many nurses should be assigned to each shift in a hospital. In this section, we will discuss four different apportionment methods: Hamilton's method, Jefferson's method, Webster's method, and the Adams method. Okay? So we start with an apportionment problem, just to explain what apportionment is. I guess one of the biggest examples in apportionment is the election of our president. And what's the Electoral College? Whenever a Democrat becomes president, the Republicans cry that the Electoral College isn't fair. Whenever a Republican becomes president, the Democrats cry that the Electoral College is fair. And it's actually the fairest way to elect a president in our country. And we'll talk about that at the end here. So, in this one right here, it says, begin by considering a problem facing First Physicians Organization, a health care provider that operates 5 medical clinics. And so your 5 medical clinics are right here, Clinic A, B, C, D, E. It says the organization has recently hired 60 doctors. Since the clinics do not all serve the same number of patients, the organization decides to apportion the 60 doctors based on the number of patients who visit each clinic in a given week. This table right here shows. So in a given week, there were 246 patients at Clinic A. There were 201 at Clinic B, 196 at Clinic C, 211 in Clinic D, 226 in Clinic E. Total 1,080 patients for the week between the 5 clinics. So this is your math right here. Now remember, they don't want to evenly distribute the doctors, because then a clinic that doesn't serve as many patients might have a doctor standing around. They want to apportion the doctors fairly so that each clinic gets the number of doctors they deserve. We're dealing with apportionment. 2 mathematical terms you got to understand is, 1, standard divisor. And I just abbreviated it with an SD. Standard divisor is taking the total population and then dividing by the number of items to be allocated. In our doctor's problem, this would be right here. We have 1,080 total patients. We have 60 doctors we're trying to allocate. So if we divide 1,080 by 60, we get 18. 18 would be our standard divisor for that problem. Second one is called a standard quota. Standard quota is taking the population for a particular group, in other words, each clinic, and dividing by the standard divisor. So what would happen here, as an example, if we take the number of patients in Clinic A, which is 246, divide by 18, and we get 13.67. And so we'd have to do the same thing for all the other clinics. So that's what this represents here. See, this is the number of patients. This is our total. We took this total and divided by our standard divisor, which was 18. Then we take that 18 and divide into 246. And now what we're going to do is we're going to take that 18, which is our standard quota, and divide into each of the clinics. So we get 11.17, 10.89, 11.72, 12.56. Okay? Now, if we add all these numbers together, we get 60.01. Sounds pretty good, because we got $60 doctors to distribute. Problem is that we can't do 0.67 of a doctor, 0.17 of a doctor, 0.89. So the methods we were about to talk about, the 4 methods, describe how we either round this number up, or round this number down, or don't round at all. And so the 4 methods are going to describe how we make these decimal numbers whole numbers so that it becomes how many items we can actually allocate, which in this case is the 60 doctors. And now we introduced 2 more definitions that are very important. It says, and this is on page 887, it says, now we introduce 2 more important definitions. The lower quota and the upper quota. The lower quota is the standard quota rounded down to the nearest integer. Now don't forget your definition of an integer in math. An integer in math is a whole number. No decimal, no fraction. The lower quota is the standard quota rounded up to the nearest integer. So lower quota is rounding down. Upper quota is rounding up. Let's talk about the first method, Hamilton's method. All right, first of all, here's the procedure on Hamilton's method, again on page 887. To use Hamilton's method for apportionment, do the following. Calculate the standard divisor of this data set, which we already talked about. Calculate each group's standard quota. Round each standard quota down to the nearest integer. So this is a lower quota that we're dealing with. Distribute any leftover items to the groups with the largest fractional parts until all items are distributed. So what it's saying here in number 3 is that once we round down, if we add them all together and we still don't reach 60, then you take the leftover doctors and apportion them to the clinics that had the highest decimal. And you keep doing that until all the doctors are gone. So using our example that we were working with, here's how we do it in Hamilton's. So 13.67 rounds to 13 because it takes the lower quota. Hamilton's method takes the lower. 11.17 becomes 11. 10.89 becomes 10. 11.72 becomes 11. 12.56 becomes 12. That's 57. So in other words, Clinic A would get 13 doctors, Clinic B 11, Clinic C 10, Clinic D 11, Clinic E 12, total of 57 doctors. We have 3 doctors left over. So what we'd have to do is we'd take the first leftover doctor and we'd look at our decimals here and we'd see that we got 0.89. So this one would get another doctor. We'd take our second leftover doctor, excluding this one. We come in and look at our decimal places. This is the next highest decimal place because this would get another doctor. Now we're at 59. We take our third leftover doctor. We can't use this, can't use this. We go to here, which is the next highest decimal place. They get another doctor. We add all this together. This is 60. This is Hamilton's method. You always do the lower quota after you calculate your standard quotas. You do a lower quota. And then anything left over, you apportion according to decimal places from your standard quota, from highest to lowest.